Hey guys, welcome to this video on wavelets analysis in R. In this video, we will understand how wavelets analysis works, what is wavelet function, and then we will use WaveletComp, which is an R package, in order to perform wavelet analysis on a series with a constant. Alright, so let's get started with some theory here. So what is wavelet? Wavelet is basically your waves. So what actually comes as a wave is oscillation. We can say these are little waves. So any wavelet function will oscillate, and we can write down an oscillating function or a wavelet function in terms of mathematics also. So let's try writing that down. So if I have a function of x where I have correspondingly plus 1 if x belongs to closed interval 0 and open interval half. This is an open interval. And minus 1 for x belongs to closed interval half and open interval 1 and 0 otherwise. So this kind of function will have breaks in between and have a range minus 1 to plus 1. So we can conclude that a wavelet object oscillate but does not decay faster. Now the question arises, why do we use wavelet analysis? So we have several of reasons to use wavelet analysis. Let us write them down and try to understand them. The first reason is it analyzes signals at different resolutions and scales. So it reads what comes up at different level of scales also, at a very small level and at a very higher level also. You can say analyze signals at different. Another reason to use wavelet analysis is capture non-stationary symbols also. So while when the function is moving, it captures what exactly its behavior is, and when the function is non-stationary also, it captures the behavior. So we can say captures non-stationary symbols. The third reason to use wavelet analysis is it uses very few coefficients but makes an efficient representation of signals. So we can say it uses few coefficient to represent symbols. I'll write to represent. The another reason to use wavelet analysis is it captures the signals which can be used for pattern recognition. So whatever the signals are coming from the waves, it captures those. So capture features symbols for pattern recognition. The fifth reason to use wavelet analysis is it can also capture and read the edge detection of images. So basically wavelet analysis is used in image processing and sensors reading. So it can use edge detection also. So we'll write can read edge detection in. So these were the reasons we use for wavelet analysis. Now we will move to R and use WaveletComp package in order to perform wavelet analysis in practical way. So I will hide this board. Alright, so let us start with our analysis. So what I'll do is, first of all, I will call the library WaveletComp. So I'll say library, and I have already installed this package. If you don't have this package installed, then you need to use install.packages and then brackets and inverted commas. You have to write WaveletComp. So I'll execute this command, and next what I'll do is I will generate a periodic time series. So in order to generate a periodic time series, I'll write xrep 1:50 length dot out equal 1000, and I will run this. Now let us understand what exactly I have done when I have used this command. I have used the function rep here. This function will repeat the sequence of number from 1 to 50, and it will create a vector length of 1000. I have also used length out argument here to actually have the desired output length of my vector. and since I have used 1000, which is way high than 50, the sequence will keep on repeating to fill the required length. So basically I have created a periodic time series here. Now what I will do is I will add little bit noise to this series. So I will write x, and this should has x plus 0.2 r norm multiplied by 100 r norm bracket 1000, and I will execute this command. Now let us understand what I have done in this. So I have used here r norm 1000 as an argument to generate a vector of 1000 random numbers from a normal distribution. When I generate from a normal distribution, it means it will have mean 0 and standard deviation 1. Next, what I have done is I have multiplied this r norm with 0.2 in order to scale the random numbers by 0.2. So this will add noise to the original vector of x I have generated. And I have also used x plus here to add the scaled random noise to the original vector x. And I have stored the result back into the variable x. Now I can also see how exactly my generated periodic time series look like. So I can plot this up. In order to plot this, I will write plot x type, then I'll write mean time series plot, then I will write xlab equal index, and I will write ylab equal value. Now I will execute this command. Now I have my time series plot here, which is an oscillating function. Let us also understand what I have done when I use this plot command. When I started with the plot function, it will create a plot for the data. I use type L in order to tell R that I am going to use a line plot. Then I use main in order to set the title of the plot. I use xlab in order to set the label for the x-axis, and I use ylab in order to set the label for the y-axis. Now let us proceed and create a data frame here. So in order to create a data frame, I'll write my.data, data.frame x equal x, and I will execute this. So we have created a data frame now. Now we will perform wavelet transformation on our data frame x, and we will use wavelet analysis. So in order to do that, I will write my.w analyze dot wavelet function my.data. Then I mention the data frame, which is x, and I'll use lewis.span, and I'll give it a value of 0. Then I'll use gt equal 1, dj equal 1 by 250, and then I use lower period equals 16, comma upper period equal 128, and then I use make dot p value equal true, and I will press this, and end dot sim equal 10. Now I will execute this. So now what it is doing is it is starting wavelet transformation, and simulation exercise is being performed. Let us break down the code which I have just written. First of all, I have used my.data in order to specify the data frame containing time series. Then I have used X, which is the name of the column in the data frame which contains the time series data. Then I have used Lewis.span equal 0. This is going to set the span for the loss smoother to 0, indicating there should not be any smooth. Then I have used GT equal 1. It specifies the time step between the observations. And then I have used DJ equals 1 by 250, which specifies the scale increment between wavelet scales. Then further, I have used lower period equals 16, which specify the lower period bound for wavelet analysis, and then upper period equals 128, which specify the upper period bound for the wavelet analysis. And in the end, I have used make.pval and I have put it equals to true, which means it should compute the p-values for the wavelet coefficient. And then I have also used n.sim and I have put that argument equals to 10, which specify the number of Monte Carlo simulation to use for computing p-values. So once I have the simulation, I can use them to plot the wavelet spectrum. So in order to do that, I am going to write wt.images my.w color.key equal quantile n.levels equal 250 legends dot parents equal list lab equal wavelet power levels MAR equal 4.7, and I will execute this command. 1 second. Alright, this okay, so this should be legend instead of legends. Let's run this one more time. Let us break down this piece of code. So I have used my.w. This is the object containing the result of my wavelet analysis. Then I have used color.key equals quantile, which is going to specify the color scale I am going to use in the plot to R. I have used quantile here to determine the colors of the wavelet coefficient. Then I have used n.levels equals 250. This argument specifies the number of levels for the color scale. A higher number of levels result in a more detailed representation of the wavelet coefficient. That is why I have used 250. So now we have our graph and I can copy this and we can move back to open board in order to understand how exactly we can read this graph. Here I will paste it here. The first thing to note here is this represent high power levels. So the color which is here and here are basically your high power levels. Another thing to note here is in these graphs, your vertical intercept represent frequency and your lower scale correspond to higher frequency. So if I am at 16, it is representing higher frequency as compared to at 128. The next thing to understand is on your horizontal axis, we have time and position. At what point of time the wavelet power level were higher and higher frequency was there. At what point of time lower frequency is there and wavelet power levels were high. We can predict using your horizontal axis. Another important thing to note here is sharp changes in the color indicate significant feature or events in the signal at a particular time and position. So if the color is changing from here to here and it's very sharp, it means there has been a significant event in this period of time. Another thing to understand here is smooth areas of the plot, which is this, is representing low noise. So we have low noise when we don't have more oscillation coming up in the wavelet analysis. Alright, so that is how the wavelet analysis graph is read. Let's go back to R and then we will create a reconstruction function in order to retain only the smooth areas. So I will hide open board. Now that we have seen the wavelet coefficient graph and we have removed the noise from the series, let us reconstruct the smooth parts of the coefficient. In order to do that, I am going to write reconstruct my.w plot.waves equal false, LWD equals C1 by 2 dot legends dot coordinates equal bottom left, and I will also say y limit equals C bracket minus 1.8 to 1.8. I will execute this command, and this command has given me my original and reconstructed series. Before we move to the interpretation of this graph, let us break down the piece of code I have written in order to obtain this. I have used reconstruct function here in order to reconstruct the original signal of the wavelength coefficient. Then I have stored it in my.w and plot it according to the specified parameters. My.w contains the results of the wavelet analysis which we generated using the analyze.wavelet function earlier. Next, I have used plot.waves equal false so that it does not plot the individual wavelet components during my reconstruction. Then I have used line width for different components of the reconstruction plot. And then I have used legend.chords equals bottom left in order to position the legend in the plot. And in the end, I have used limit for y-axis of the plot. So let us copy this graph and move to open board in order to understand how we can read this. So this graph actually assesses the effectiveness of our wavelet analysis in reconstructing the original signal. So what we did is we had the original series, we added noise to it, and then we have reduced the noise and plotted the smooth part of it in order to understand how the reconstructed signals capture the feature of the original series. Ideally, this type of reconstruction signal should follow the pattern of the original signals and with variation reflecting the noise and details captured by the wavelet analysis. So in our case, if we see, we are actually using the original series and then reconstruction is following almost the similar kind of pattern for us. So we can say the analysis we did here in order to create a reconstruction series for our wavelet analysis was fine. Alright, I think that is all for this video. What we did in this video is we created a periodic time series, then we added noise to it, and then we reduced the noise and reconstructed the series in order to see how a wavelet analysis performs and what signals can be captured with our estimation in contrast to the original series. An important point to note here is that we have used here a series with a single constant. In the upcoming videos, we will see more of wavelet analysis and try to understand how we can use multiple constant and variables in order to perform wavelet analysis. Alright, thank you.